Okay, so now we're going to talk about an ideal gas. Basically, it's focusing the content of equation of state of an ideal gas. So first, I would like to say something about experiment related to this ideal gas. Uh, at the beginning, what happened is that there were three scientists. One is Robert Boyle, another one is Jacques Charles, and last one is Gay-Lussac, no, Joseph Gay-Lussac. So these were the three scientists who did experiment in volume, pressure, and temperature. So in the first, the one who did experiment was Boyle's law. Okay, so talking about Boyle's law here. So what Boyle's law states that is volume of gas is inversely proportional to pressure. You know, inversely proportional to pressure held at constant temperature. Okay, so at constant temperature. So let's say an example. Let's discuss this relation. When the volume is increased, pressure goes decrease. Let's take example of air pump. So when we pump air, imagine the molecules inside pump get the volume of the molecule get decreased and the pressure increase. It means that when the volume uh, so when the volume is increased, the pressure get decrease. Means when we pull off the pump, the volume get increase but the pressure get decrease. So means but when we increase pressure, the volume get decreased. Like here is a pump, and when we increase the when we decrease the volume, so the pressure get increase, like that. So this is the relation of Boyle's law. So it can be also written in PV equals to constant. This is given by Boyle's law, and for this another way of writing equations. Some numericals you can even write like PV P1 V1 equals to PV P2 P2. So this is the mm, uh, so this is the initial pressure and initial volume. Another one is final pressure and final volume at constant temperature. So you must have to remember that P1 is the initial pressure and P2 is the final pressure and final volume at constant temperature. Must remember at constant temperature. So uh, when the statement is constant temperature, you must have to think about this relation. Okay, don't get confused. We'll be discussing about Charles law again. Okay, previously I talked about Boyle's law. So there we discussed about relation between volume and pressure. That is, volume is inversely proportional to pressure. When pressure increase, volume increase. When pressure increase, volume gets decreased, and when volume increase, pressure get decreased. We took example of that air pump. So here is the different part about Charles law. So actually the main theme of Charles law is about the liquefaction of gas. So how the gas is how gas gets liquefied. So we'll discuss about that point. Okay, so gas liquefy when temperature get reduced. Means here I have written one relation between liquefaction of gas on the temperature. So here you can see here. So when the liquefaction of gas gets increased, the temperature gets decreased. So you can take the example of a gas cylinder. When there is little gas, when means when sorry, I want to take like so I just want to take one example of, let's say, whatever. Okay, so so not this, I'll say a different one. So okay, when the temperature increase, when the temperature gets increased, the liquefied gas get decreased. Means you can simply say example of pressure cooker. So when you increase the temperature, the gas molecules gets decreased. Means they get expanded. The molecules inside the pressure cooker get expanded. So when the molecules get attached, uh, compressed, the temperature gets reduced. Means like when the molecules get into a solid, the temperature gets reduced. Means it all depends on the molecules. Okay, so back to the another one is about graph. So means here is the one relation about Charles law. So here we can see where you can see here that um, mm, the relation of volume and temperature. When the volume gets increases, okay. So when the volume gets increases like this increases, this is the increases, okay. Increases when the volume gets increases. When the volume gets increases, the temperature also get increases. Here you can, volume is directly proportional to temperature. When the volume get increases, temperatures can also get increases. So from minus 273 to 100 degrees Celsius. When the volume gets increases, the temperature also get increases. So but T means thermodynamic. Okay, so on the down I had written the thermodynamics. T means thermodynamics, don't get confused. T is the thermodynamic temperature. All right, it's thermodynamic temperature. So but whenever you need to do calculation, you first remember there must be initial and final. So these are the initial volume and initial temperature, and this is the final volume and final temperature at constant. Final final volume, final temperature at constant temperature. Okay, so this is about Charles law. uh, okay, so here you go. So this is a Gay-Lussac's law. So we have studied uh, two laws. One is Boyle's law, Charles law. So here we go with Gay-Lussac's law. So in this law, what it states that is pressure is directly proportional to temperature. Means when the pressure increases, the temperature also get increases. So these simple things. Is here you can. Here is the graph. When the pressure increases to, and the temperature also get increases. It's like and then we have a relation here. uh, this is the relation of this P1 T1 is the initial pressure and temperature, and this is P2 T2 is the final pressure and temperature at constant temperature. Okay, so so this is the concept of Gay-Lussac's law. So I have to remember the whole thing. So previously we discussed about Boyle's law, Charles law, and Gay-Lussac's law. So let's to combine these three equations from three scientists that did experiment on the pressure, volume, and temperature. So let's do revise. This is the Boyle's law, and this is the Charles law, and this is the law of pressure. You can even say uh, Lussac law too. So don't get confused. So in Boyle's law, this is about the volume is inversely proportional to pressure. So when the volume gets increased, the pressure get increased. So in the next in the second equation, we discuss in Charles law about between volume is directly proportional to temperature. So when the volume get increased, the temperature also get increased. So in next part, in the final, in third equation about law of pressure, Lussac's law, it is you find out about the pressure is inversely proportional to temperature. So when the pressure get increased, the temperature get increased. So combining these three equation in pressure, volume, and temperature, so we get uh, mm, mm, PB is directly proportional to temperature. So when the pressure volume increases, the temperature also get increases. Okay, so here we get one what is a ratio. Okay, ratio. So we get this from this. Okay, so this is the initial pressure, volume, temperature, and this is final temperature. You'll study. So you'll just do this in calculation. So this is this law relates to a fixed mass of volume. Means this law relates a fixed mass of volume. Fixed mass of gas, not volume. This is fixed mass of gas. Okay, so this is the that one. So beside that three experiment which has done by three scientists, so here we have another experiment of how the volume of gas held at constant pressure and temperature depends on the mass of gas present. So sometimes you also need to calculate the mass of gas present in certain containers. So we're going to discuss it. The main part we focused is about what is the point about the mass of gas present. So it is found that volume is directly proportional to mass. So when the volume get increases, the mass also get increases. So this is the relation, mass of gas present. Okay, so this is the mass of gas present. So here is one relation that uh, PV is directly proportional to mass times temperature. So this is the mass of gas present, and this is the thermodynamic temperature. Okay, this is the thermodynamic temperature. Don't get confused. Okay, so this is the so in another experiment we came to know about the pressure volume is directly proportional to mass of gases present times temperature. So next we have, so here let's take one AMT. Yeah, we took A as a constant proportionality. Yeah, constant. Let's take a constant proportionality. Yeah. This is the constant proportionality. Mm, so like that. And then after I'm gonna go to the Avogadro constant. Okay, so I'm just gonna discuss about the Avogadro constant. So let's drop this one first. I would like to discuss about the Avogadro constant. So okay, Avogadro's constant. Avogadro constant means N equals to 6.02 into 10 to the power 23 per mole. Okay, the 23 per mole. Um, uh, and then Avogadro 20 per mole. So what is Avogadro constant? Avogadro constant is the number of atoms in 0 point. So okay, 0.1. Sorry. Okay. Here, let's not wrong. What happened? Okay. It's not wrong. It's 0.012 0.012 kg of carbon 12. So Avogadro constant is 0.02 kg of carbon 12. So that's it. So it's the number of atoms in mole of atoms. It has value here 6.02 into 10 to the power 22 per mole. You'll study this in chemistry, so you don't have to get worried about this in physics. So and then after returning to uh, uh, returning returning to the three gases laws and using the number of moles of gas. So here we'll study next. Okay, let's go next slide. So here means returning. So returning to three gases laws, and using the number of moles, of gas. Okay, so using the number of moles of gas, so we have PV direct in proportion to NT. Okay, NT, and means moles of gas. Okay, so this is the moles of gas. So in last slide we discussed that PV equals to EMT. That is about finding the mass of gas at present. Mass of gas at present. Don't get confused. That is about the mass of gas present. And this is of moles of gas. Okay, this is the moles of gas. This is the moles of gas. So by you can even write like nRT. This has done by the great scientists. We didn't do that. So n R means a constant proportionality. This is the constant of proportionality. IONALTIONA. Okay, proportionality, let's say like this. Okay, this is the constant proportionality. So n means a number of moles of gas. Okay, number of moles of gas. So okay, so where R is molar gas constant. Okay, molar gas constant, or universal gas constant, or universal gas constant. Okay, this is the universal gas constant. So the value of R is 8.3 joule per Kelvin per mole. Okay, per Kelvin per mole. So uh, this is PV is directly proportional to NT, where N is the moles of gas, number of moles of gas. So where nt is number of moles of gas and pv equals to nRT. Get remember, so this is the important formula you need to do in your calculation. This is most important. Okay, so pv equals to nRT. So where n is the number of moles of gas, pv equals to pressure, volume, t is thermodynamic temperature, and then r is constant of proportionality we took, and where r is the molar gas or a molar gas or universal gas constant. Okay, universal gas constant. So so let's do okay. Okay, so sometimes the equation pv equals to nRT is expressed in the form of let's explain. So sometimes pv equals to nRT is expressed in the form of in the form of where is my in the form of ppm equals to RT. Okay, so ppm, so where this pm is the molar volume. This is the molar volume. This is the molar volume, means volume occupied by. So okay, what happened? So this is the volume um, volume occupied by 1 mole of the gas, right? So volume occupied by the 1 mole of gas. So R2 we had already discussed. This is the universal gas constant or molar gas constant, and then the value is 8.3 joule per Kelvin per mole. Okay, so V means the molar volume. So sometimes you need to find the answer of let's do calculation of molar volume. So how you're gonna do it is just use ppm equals to RT and extract from pv equals to nRT. So like that. Okay, so don't get confused. So another version. Okay, so another version. So in another version we have pv equals to nkt. This is the pv equals to nkt. So where k is the Boltzmann constant, uh, Boltzmann constant, yeah, and this is the Boltzmann constant, and this is the n means number of molecules in the gas, present in gas, gas, and so where value of k equals to 1.38 into 10 to the power minus 23 joule per Kelvin. So this one, so I just want to say, so how n k means n equals to just remind me, just wait for a while. So I want to explain how to find the value of n. Yeah, so here is the in chemistry I got n into n. So this is the Avogadro's constant, and n is the number of moles. Yeah? Number of moles. Right? So n is the number of particles. Number of molecules, number of particles, the same things. They are the same things. Okay. So PV equals to nkt. So this all formula is used mostly in calculation part. So on a certain condition, like if you were asked to find the pressure, under so if you were asked to find the particles or molecules present in gas. So how you calculate this? You'll use this equation. Okay. So one last equation we have, and that is about the molar gas constant R and the Boltzmann constant K are connected to the Avogadro constant. So they are connected means the so R R is the molar gas constant. R is the molar gas constant, and K Boltzmann constant. Boltzmann constant. Okay, Boltzmann constant are connected to Avogadro constant. Are connected to Avogadro constant is Na. Don't get confused. So here we have equation equals to R by Na. So Boltzmann constant is equals to R upon Na. So Avogadro constant. So R is the molar gas constant. So if you're given to ask about the molar gas constant, like R, molar gas constant R. So you're gonna calculate just using this like R equals to K times N, yeah, like that. Okay. So these three laws are for real gas. Okay. So so these three laws, we study about the three laws about Boyle's law, uh, Charles law, and law of pressure. So the three laws are for real gas only if the sample is not too great. If the sample is not too great, and sample is not too great, if the gas is well above its liquefaction, or if liquefaction of temperature, but they can be used to define ideal gas. So here the word they can be used, they can be used to define idle gas, so idle gas. So here the story comes. So idle gas, so this is about idle gas. you know so all equation we had is studied now till is all about the idle concept of idle gas. So I'm gonna describe idle gas. Okay. So all the formula, all the laws we discussed till is all about idle gas. Here is the discussion about idle gas. So what idle gas? What actually idle gas? So idle gas is one who follows the equation of PV equals to nRT, but at all pressure, volume, and temperature. So pressure, under pressure, volume, and temperature. You can just say that. What do you mean by idle gas? Idle gas is the one who follows the equation of PV equals to nRT at under pressure, volume, and temperature. You can simply say like that. So so this is the reality of idle gas. How idle gas comes. Idle gas comes from the history, like say about Boyle's law, Charles law, and law of pressure, like that. Okay. So let's to revise that what we study at the beginning. So at the beginning, we know that in Boyle's law, we know volume is inversely proportional to pressure, and we get some equation that is uh, mm, Pt equals to B2. At first, we discussed about in Boyle's law, volume is inversely proportional to pressure, where the equation can be written in volume P1 B1 equals to P2 B2, and this is the initial and final one. In second, we uh, discussed that volume is in Charles law. This volume is in Charles law. This volume is directly proportional to temperature. So we can write that in equation from T1 T2 equals to B2 T2. Okay, so no, this can be also written as PV equals to constant. You know, say about it's also PV equals to constant. So like that is volume is directly proportional to temperature. So in law of pressure, that is pressure is inverse directly proportional to temperature, that is uh, P1 upon T1 equals to P2 upon T2. You can even say like that, P1 equals P2, T2, T2. Okay, so so this we discussed in the first in law in three laws of gas. So combining these three equation under gas laws under pressure, volume, and temperature, that we get is equals to this, and this can be written like P equals to T1 equals to P2 B2 upon T2. So this is the final one, and this is the initial one. Okay. So next one is in another experiment which is about uh, in mass of gas present, that is PV is inversely proportional to mt. That m is the is the mass of gas at present, and this can be even written equals to in an equation form mt, and a is the constant at proportionality, and we use about the Avogadro constant. Avogadro constant is 6.02 into 10 to the power 43 per mole. Okay, so so in uh, and then after we discussed about PB inversely proportional to anti, PB equals to proportional to anti, where so okay, let's do up this. Okay, so discuss. So returning to the number of moles, we get PB equals inversely directly proportional to NT, where N is the constant proportionality, and PB equals to nRT, where uh, where N equals to where N equals to number of moles, number of moles of gas, and then R equals to constant proportionality, where the value of R equals is 8.3 joule per Kelvin per mole, per mole. And sometimes equation can be also expressed P equals to nRT in the form of PVM-RT, PVM, where Vm is the molar volume, molar volume is volume occupied by 1 mole of gas. All right, so then let's drop this. Okay, so I'm gonna say something about another version. So we did revision in another version, so this takes too much time. How much time this will take? All right, so in another version, this was about PB equals to NKT, where N is the number of moles, where N is the number of molecules, in the gas, number of molecules in the gas. So R is the Boltzmann constant, Boltzmann constant, Boltzmann constant is K. Yeah, okay. Sorry, is the R. Okay, so no, this is the NKT. Sorry, this is the NKT. Okay, so PV equals to NKT. Don't get confused. NKT is NKT. So K value is 1.38 10 to the power minus 23. Power minus 23 joule per Kelvin. Okay, so R and K is connected through Avogadro constant. We discussed about R equals to N. Sometimes you need to find the N, and N can be equals to N into Avogadro constant equals to N into N. So okay, so this is the division part, and we discussed about the ideal gas. So one will always the equation of state P because energy under pressure, volumes, and temperature. Okay. So let's do numerical about ideal gas. So the question here is find the volume occupied by 1 mole of air at standard temperature and pressure 273 Kelvin and 1.01 into 10 to the power 5 Pascal PA Pascal pressure. Okay, unit of Pascal pressure, taking R as 8.3 joule per Kelvin per mole. So which equation you're gonna do here? So here pressure is mm, sorry. So here pressure is given. You know. Sorry. Yeah, pressure is given and temperature is also given. Temperature is also given, and R equals to also given, and 1 mole means we have PV equals to nRT. So you can find the volume. To find the volume, you can just use PV equals to nRT. So B equals to nRT over P. Okay. So here you can just do uh, 1 point the value of 1 mole. So 1.0 into 1.0 into the value of R means 8.3 R 8.3, and the temperature equals to 273 over pressure is 1.01 into 10 to the power 5. So the answer is uh, 2.24 into 10 to the power minus 2 meter cube. Okay, 2 minus 2. So sometimes you need to convert one concept about converting Celsius into Kelvin into Kelvin. So how you can do it? So Celsius plus 273 equals to Kelvin. Okay, so remember this. So this is the concept of ideal gas. So I'll discuss uh, about the kinetic theory in coming slides soon. All right.